With the tools we found in the previous parts, we can now formulate the testing algorithm for upward planarity. This is our theorem 3. So we have a graph that's an acyclic plane digraph, where the embedding is given by the sets of faces and the outer face. Then we can test if it is upwards planar, respecting the embedding. And to test this, we only check if G is bimodal and there exists a consistent assignment. To prove that it's correct to go from here to here, we can do everything as we just constructed. But the interesting part is, if it is bimodal and we have a consistent assignment, how can we prove that it's actually upward planar? And for that, we first want to construct a planar ST digraph that's a supergraph of G, and then apply the equivalence from theorem 1. So reminder, it among others said that a graph is upward planar if and only if it's the spanning subgraph of a planar ST digraph. We will now state the so-called refinement algorithm. Given a consistent assignment, the sets of faces, and the outer face, we construct an ST digraph. Let's have a look at a face. We want to consider the clockwise angle sequence of the large and small angles on the local sources and sinks. So for example here we could have a small angle, large, small, small, large, small. The goal is that we want to add edges to break the large angles that we have. And we know the large angles correspond to the global sources and the global sinks. So let's say we have our face, it's an interior face, and we have an angle sequence of at least 2. Then at some point it must contain an L. And there are more S's than L's, so at some point we must have this subsequence LSS. The only way to not get it is that for every S we have an L afterwards, but then we must have the same number of large and small angles, which we don't. So let's pick such a subsequence, for example here. We have 3 vertices, X with a large angle, Y and Z with the small angles. We now want to add an edge. First assume that X is a source. We want to insert an edge from Z to X, like this. And now this large angle here is destroyed. It has neither a large nor a small angle, and it is not a global source anymore. Now let's have a look at this face. We again have an L here. This is a global sink. And this becomes our X, this our Y, our Z. We again want to add an edge between X and Z, but now in the other direction. Now again, if we look at this large angle here gets split, and the 2 new angles are neither small nor large, and this is not a global sink anymore, so we removed it. And now we have this supergraph where we just added 2 edges, we eliminated all the large angles, and we got rid of all the global sinks and sources that have their large angle at this face. And since every global source and global sink must have their large angle at some face, we can get rid of almost all of them, except of those that are on the outer face. And then we just have to refine the outer face again, and there we have to make sure that we keep 1 global sink and 1 global source. And how to do that you will show in the exercise. Now if we refine all faces, then G is contained in a planar ST digraph. And the planarity, the acyclicity, the bimodality, they are all invariants under construction. It's easy to see that we can never create a directed cycle, we will never create something that's not bimodal, and we will never destroy planarity. Let's have a look at another example. So we have our assignment here, we have the large and the small angles, and we pick subsequences of LSS, for example here. We have LSS, we want to create an edge from here to here, and now this becomes a small angle, this L is destroyed. We have LSS here, we create this edge, this global sink gets destroyed, we get two small angles here. We can take these LSS, we add an edge up here, we destroy this large angle. Then we add an edge from here to here. We add an edge from here to here. And an edge from here to here. And now all the large angles in the interior faces are destroyed. We pick a source and a target on the outer face, and we keep refining while keeping those. So we add some more edges here, and then we're done. Let's summarize our result. For a combinatorially embedded planar digraph, we can test in quadratic time whether it is upward planar. And for the proof, we first test if the embedding is bimodal. Then we test for a consistent assignment via a flow network. If it is bimodal and a consistent assignment exists, then we refine it to a plane ST digraph. And we draw that plane ST digraph upward planar. Then we only have to delete all the edges that we added in the refinement step to get a drawing of our input graph. So for embedded graphs we can do it in polynomial time, but for non-embedded graphs it's NP-hard. Still, there are some algorithms. There are some fixed parameter tractable algorithms to test upward planarity for general digraphs. And the parameter is the number of tri-connected components. So this is an algorithm that's polynomial if the number of tri-connected components is constant. So it depends on some polynomial of n and some function of this parameter. And that can be exponential, super exponential, whatever. And finding assignment in theorem 2 can even be sped up. So instead of using this flow network, we can use an algorithm by Abbasi, Healy, and Rexton. There we only need order of n plus r to the 1.5, where r is the number of global sources and sinks. So if this is very small, then we can do it even in linear time. And there are many related concepts to this. Quasi-planarity, that's something you will hear about in the last lecture. Upward drawings of mixed graphs. Upward planarity on cylinder, on the torus, and so on. And in the next lecture we will extend this upward planarity to drawing of graphs that are neither planar nor acyclic, but we still want to draw it as upwards and as planar as possible. Thank you for watching.